So with all the different techniques that we have seen in terms of what can be done to improve the efficiency of systems, one of the things that sort of comes out as a overall takeaway is that there is a need for so-called optimization, right? Now, again, the dictionary definition of optimization is an act, process or methodology of making something such as a design, a system or a decision as fully perfect, functional or effective as possible. Okay. So, you will note that it's basically saying it's not about getting the best possible solution, it is getting something as perfect as possible. There are obviously limitations to the system, to whatever you are trying to build, right? Are you designing a particular new object or an embedded system or any kind of system, or just taking a certain kind of decision that affects, has multiple inputs. The point is, whenever you are dealing with real life scenarios, there are multiple different input variables as well as outputs that get affected, and there is very rarely a scenario where an optimum is an actual global optimum where you can say this is the best possible thing that I can do. Hence the terms as fully perfect as possible, right? You want to sort of define certain kinds of cost metrics, certain kinds of optimization criteria, and try to see how well you are able to do on those, but in general it's impossible to guarantee that this is the best that can be done. Now, in the context of an embedded system, typically what we are looking to optimize are metrics such as this, right? The speed, how fast does the system run or how fast does it respond to events or inputs. How much is the area, which could be the size of the device, or it could be how much memory does it require if you are looking at software, right? And of course, what's the battery life, how long does it last on battery, or how much power does it consume, which means does it get very hot, right? And of course, the one big unstated term over here is the overall cost of the system, right? So now comes the question, how do we go about optimizing all of these things, right? What are the sort of knobs or the keys that are available to us to even change any of the parameters over here and thereby explore different possible options in terms of optimization. Now, one of the first and foremost is what we call algorithmic optimization, right? And what we mean over here is, how do you choose the most efficient algorithm for the task that we have at hand, right? And an example of this is, let's say you are given the task of sorting a set of numbers. Sorting basically means that you are given a set of numbers, you need to put them in a sorted order, either from the lowest to the highest or highest to lowest, right? Now, sorting is a very well studied problem in general, and there are multiple different algorithms that exist for it, right? Some are very simple to implement, some are significantly more complicated to implement, but turn out to be very fast and efficient in practice, okay? So, as an example of this, I am just going to take up a small piece of code. This is not embedded specific, right, because sorting is not really something that's embedded specific at all. So, what I am going to show is a demonstration of a small piece of C code which implements a couple of different sorting algorithms, and then let's sort of try and understand the results that we see over there. Alright, so the code that you see on the screen over here is, this is a regular C program. What it implements is one function called bubble sort. Now, if you are not familiar with what bubble sort is, then don't worry about it, I am not really going to get into the details. At a very high level, what it's doing is, it sort of sorts numbers by trying to bubble the lowest numbers up towards the top. So, you think of it as a list of numbers that you have from top to bottom, and what it does is sort of scans through the numbers one by one, and as it goes through, it pretty much takes all the other numbers that are there, and what it does is it tries to either take the smallest number and bubble it up to the top, or it takes the largest number and keeps pushing it down until it has reached the bottom, right? And at the end of the day, what it does is, there are also some optimizations out here which sort of say that yes, I have actually done the proper swapping, I have finally managed to get the particular number to its correct destination, and thereby I am able to go through and take the numbers one by one and get them to the point where they should be. Alright, so that's one particular way of sorting. Like I said, explaining how it works and why it works is not in the scope of this course, but I strongly recommend that you take a look at sorting algorithms, because they are good ways of understanding what computers can and cannot do efficiently. One thing that we can say just from looking at this code though is there are two for loops. The first for loop runs from 0 to n minus 1, and the second also possibly runs up to n minus 1 in the worst case, right. So if I just think about it, I can imagine that the work over here is going to end up being proportional to n into n squared, okay. And in fact that is what is called the algorithmic complexity analysis of bubble sort, which says that typically bubble sort is expected to operate in order of n squared time. If n is the number of elements that I am trying to sort, then it would take about n squared time in order to actually sort the numbers. Now there is another variant of it which is actually very simple, which is called insertion sort, right. Once again, the differences between bubble sort and insertion sort are more in the way of how they are implemented, right. What insertion sort tries to do is pretty much pick a particular value and insert it at the correct place where it is supposed to be, right. Pick the smallest number, put it in the first place, pick the next number, put it in the next place after that, and so on, okay. Very similar, if you look at it, it has one for loop out here, and it also has another while loop, which if you look carefully through the different options over here, you will realize that in the worst case this is also going to operate up to n times, right, which means that from a complexity theory point of view, this is also an order of n squared algorithm, okay. Now what that means is I have two algorithms now, bubble sort and insertion sort, both of which are expected to operate in O of n squared time. Now the third algorithm that I have, I am defining it as basically something called hybrid sort, right, which says that if I have a small insertion sort threshold over here, right, or rather a small number of values to be sorted, I am just going to use insertion sort and say that that's fast enough. If not, I will use something called quick sort. Now this quick sort is one of the most famous algorithms because it is something that works extremely well in practice for sorting numbers, right. It has a algorithmic complexity of O of n log n. So if n is, let's say, 1000, log n to base 2 is roughly around 10. So this takes more like around 10,000 operations as opposed to the 1,000,000 n squared operations that bubble sort or insertion sort would have taken, right. So by the time you hit something like n is equal to 1000, you expect quick sort to be close to 100 times faster than the others, right. Now is that really the case? Well, there might be other factors that weigh in, and you might not get an improvement of exactly a factor of 100, but in general quicksort is definitely the way to go if you actually want to sort a large set of values. Now I could have just used quicksort itself directly over here. The hybrid sort is sort of used in order to convey that for small values of n, you are probably better off not using quicksort, because just the setup and overhead of doing quicksort means that it ends up being slower. But again, quicksort is a library routine available as part of the C libraries, so I am just using that. I am not even sort of doing anything extra out here. Now the interesting thing is the experiment that I am going to run is basically generate a random array and measure the execution time for a particular sorting operation to be done, right. So the setup is done over here, right. I basically create a couple of arrays out here, and I basically go through a number of different array sizes, right. And what I do in this case is, in each of these cases I generate a random array, I make a copy of it, I measure the execution time of bubble sort, then of insertion sort, and then of the hybrid sort, and print all of those values out, okay. So let's run this through. In this case, for the last value, rather than going up to 100,000, I am just going to limit this to about 50,000 because it starts to take a little longer than what I would like on a machine like this, okay. In fact, yeah, maybe just make it around 30,000 or so. And what I am going to do is just compile this, right. Yeah, so it's already compiled, right, and I can run it, right. So the compilation and running, hopefully all of you recall from the C programming itself, right. It's a very straightforward thing that I'm doing over here. The make command that I used over here is, I haven't actually written a make file, it just turns out that by default, if I run make with the name of an executable and it finds a C file with the same base name, right, it actually just runs the command cc in order to create this output, and that's good enough for me. Okay, so now what should I expect to see? Bubble sort and insertion sort are both order of n squared algorithms. I should expect that both sort of take similar amounts of time. Quicksort I do anticipate is going to run much faster, so let's give it a shot. And it's sort of already run through fairly fast, right? So I'm just going to quickly go through this. For an array size of 10, you can pretty much see that it doesn't really matter. These things are running in microseconds, right? So they're extremely fast. At an array time of 100, things are still extremely fast. This is like 35 microseconds. It's almost at the point where your measurement accuracy is, you're talking about close to round off noise over here, right? But you can see a pattern already starting to emerge, which is that bubble sort is actually taking longer than insertion sort. So even though they are both n squared, in this case I can see that insertion sort is almost 3 times faster than bubble sort. Okay, and that trend continues. When I go to the size 1000, I find that yes, I'm still maintaining that factor of 3. Now you can really start to see a difference between at the size of 100, you can actually see that the insertion sort and quick sort, because quick sort is what would have applied over here, they actually end up taking almost the same time, right? It's even possible in some cases that insertion sort is slightly faster than quick sort for small enough numbers. But by the time you get to 1000, right, I can see that insertion sort is about 6 times slower than the hybrid sort, which is basically a quick sort at this point. Now if you recall, what I said was for n is equal to 1000, I actually expect that this should be 100 times faster, not 6 times, right? And the point is, it's not 100 times faster because there are a lot of other overheads associated with quick sort. It is still faster, but not by a factor of 100 as we predicted to start with. What happens when we go to 10,000? At that point, I find that my factor of 3 between bubble sort and insertion sort still holds. At this point, quick sort is hugely faster, right? I mean, now it's like a factor of 100 or so faster than what we were considering, than the insertion sort. And at 30,000, bubble sort is more than 3 times slower than insertion sort, right? And this is now like orders of magnitude faster, quick sort. Okay, so what's the point over here? The point that I'm trying to make is the algorithm that you choose makes a big difference in terms of the running time. Okay, that's good. It means that you choose a good algorithm, your things will run faster. It also means that even among algorithms that are otherwise looking similar, both are n squared, bubble sort and insertion sort both have n square running time, it turns out that insertion sort is faster. Now why is that the case? On average, it turns out that insertion sort actually ends up performing fewer swap operations than bubble sort. Now this is not something that comes out very obviously by looking at the code, but you can actually do some kind of analysis and over that find out that insertion sort actually turns out to be more effective. It makes more effective use of the comparisons and swapping that it does. The long and short of that is that from a pure computation point of view, the time point of view, in general, if you need to choose between bubble sort and insertion sort, you are better off choosing insertion sort. However, if you have the choice of doing quick sort, you should just go ahead and use that, right? Now, there is a secondary aspect to this which is not so obvious, but actually does play an important role, which is it's not just about the time, right? What is also happening over here is there are actually computations, comparisons, and there are memory accesses, both of which consume energy. Every value that is loaded from memory into a register or taken from a register and stored back into memory involves activating the bus, activating a whole bunch of pins for communicating with the outside memory, transferring data, which involves switching of various wires from 0 to VDD and back. And if you are able to reduce the number of memory accesses, which in turn of course translates into reduced time, you do get a reduction in the amount of memory as well, or rather the amount of power being consumed by the system as well. One more aspect which is related is the fact that if I have an algorithm that really runs very fast, right, it is possible that during the time that it runs fast, it actually consumes a lot of power, maybe because the instructions it uses are somehow activating more memory blocks or something like that. But the point is, it does its work very quickly, and then you can actually put your CPU into deep sleep, perhaps, right. It might be very well that such a scenario actually ends up consuming less energy in the long run than something which takes lower energy but actually takes a much longer time to run, right. So all of these are sort of secondary effects of the choice of your algorithm, and knowing how to choose the right algorithm, of course, in some cases it's obvious just from the performance point of view, but there may be secondary considerations that make it such that you actually choose something which is better from a power point of view, even though it looks like it's not particularly good from the speed point of view, right. You choose it because it's just something that can be run very simply, and it's a simple code which maybe can run completely from the cache memory and therefore reduces the amount of accesses to external memory and thereby reduces the overall power consumption. So all of those are sort of secondary effects that need to be taken into account as well. Okay, so after looking at algorithmic optimization, the next kind of optimizations that we can think about, one of them is what's called memory optimization, right? And this is basically how do we make efficient use of memory, which could be the RAM associated with the system, but also the flash memory, which is the non-volatile storage, which can still be used in order to store data, right? But primarily would be used in order to store the sort of non-volatile or data which does not need to change very often. Now there are interesting things that happen here, one of which is the fact that even given that flash is a read-write kind of memory, you can both write data into flash as well as read from it. Sometimes there may be a temptation to just take the data that you are receiving and store it into flash straight away. And it turns out that from an energy point of view, that's probably a bad idea, because writing something into flash memory is going to consume significantly more energy than having something which is just written into local RAM. Another thing which is kind of interesting is the fact that depending on how you choose your data structures, you might end up being able to have your entire data structure stored in cache memory, right, for the duration of your computation. And only when the entire computation is completed, actually it needs to get stored out into the main memory. Cache memory is usually smaller and closer to the CPU, which also means that the energy required for reading or writing cache memory is typically less than that required for reading or writing main memory. So even from a power or energy point of view, you might find that if you are able to reduce the amount of memory that you have or that you need for your computation, then you can actually save on power. Interestingly enough, sometimes just the choice of a data type can make a big difference. Very often people just tend to use a data type like int, or even worse is actually something like float or double, right? Float for two reasons. One is, of course, it takes the same amount of space as an int, but in terms of computation, the floating point hardware is significantly more complicated, right? It is slower, it consumes more power than what can be done with integers. So if you can do something with just integers, you are better off. In fact, if you can just do something with 8-bit integers, that's even better than doing something with actual full 32-bit integers, right? Not only does it occupy less space in memory, it also occupies less space in cache. It becomes easier to access, right? The sort of strain on your bus when you're trying to load or store data is less. Strain, of course, being a not quite accurate term, but yeah, the point is that you are putting that you are requiring less toggling of the bus in order to access the data. CPU code, the code that actually runs on the CPU, there are many different optimizations that can be run on this, right? And typically compilers play a very important part over here. A very simple example of one of the kinds of optimizations that you can sort of think about is something like this. What actually happens over here is that this is using a transformation or a change in the code which is called loop unrolling. And the purpose of this loop unrolling is basically what it's saying is that I have some kind of processing that I need to perform, right? And I'm putting it in a loop over here, and I'm going to call that processing 100 times, okay? Now, if it is such that the actual work done in the processing is relatively small, right, or just a couple of computations, you might actually end up in a scenario where the overhead associated with this for loop, which after all requires, take the variable, increment it, compare it against 100, and then decide whether to branch or not, right? You are now doing that 100 times. Instead of that, I rewrite the code this way, where what I do is I call process with different index values, I plus 1, I plus 2, I plus 3, and each time I increment this I by 4 instead of by 1. What that means is that the for loop by itself runs only 25 times, right? Of course, the work done is the same. I still have to call the process 4 times for each of the 25, which means I call it 100 times. But like I said, at least the overhead associated with the for loop can be reduced. Similarly, using fixed point arithmetic instead of floating point, there are a number of different optimizations, some of which can be automated, meaning that the compiler can directly step in and help you with it, but some of which you as the designer need to be able to take a call whether it's possible to rewrite the code in a certain way. Compilers play a very important role over here, which is that typically compilers have many flags that can be passed into them in the compilation process, which can specify different kinds of optimizations. So something like loop unrolling can actually be specified as a flag to a compiler, suggesting that the compiler should try and unroll loops if possible. Or it might say don't unroll the loops because I want to keep the code size small. Or there might be some other things which talk about certain other kinds of optimizations that can be run on code. So understanding the flags that are available to you when you use a compiler can make a difference in terms of how good the code that you finally write or that you finally deploy ends up being. As far as possible, as a designer, you should also try to simplify computations, eliminate redundancy, right? In some cases, the compiler can help you with that in terms of identifying redundant code and so on. But again, the big picture is with you as a designer. There are optimizations that are specific to the kind of cache memory and the memory layout that is available for your system, right? And certain kinds of compilers are even aware of that and can make use of that. But once again, this is a place where a good designer will be able to make better choices, even in terms of the sizes of the different data types and so on that are being used in the system. And finally, compilers play an important role in terms of choosing the right kind of instructions, right? Even though we say ARM, what we actually mean is a whole family of different processors that have the same base instruction set but have a number of different enhancements on top of that. A good compiler will be able to sort of identify that this is the specific family variant that you are looking at, and then pick instructions that are efficiently implemented for that particular variant or that even exist only in that particular variant, right? Because if you are sure that you are only compiling for one particular family of or subfamily of processors, then it makes sense to optimize as much as possible for those processors. There are other optimizations. IO optimizations are one, and the obvious thing, as we already discussed while talking about DMA, is that if possible use DMA to handle data transfers instead of a CPU driven IO, right? And what do you do over here? The CPU could either go to sleep or it could handle some other computation during the same time, either reduce the total amount of time required for the computation or at least reduce the power being consumed by going into a low power mode. Similarly, we already looked at a number of different power optimization approaches. Primarily, those would consist of things like sleep modes, reducing clock speeds, turning off unused peripherals and so on, right? But what can actually be used would ultimately end up being very specifically dependent on the choices you have made in your system. A very directly related term over here is simply the duty cycle, right? The way you write the code and the kind of algorithms you choose would impact the duty cycle of how long each device or each component of your system is awake, is active versus in sleep mode, and that will make a difference to the overall average power consumption. And finally, code size optimization, right? I mean, how do you actually make sure that you can optimize your code to fit within available memory, right? Removing unused code, using all the kinds of compiler optimizations that are possible. In other words, understanding the tools available at your disposal makes a big difference in terms of how you make use of the final system. So, to summarize this part about optimization, right, a full system level understanding is needed for optimization. You cannot just make choices in one area without considering how they will impact other areas. For example, using a small CPU might end up giving you low power consumption, but on the other hand it might become so slow that you end up spending more time performing computation. Perhaps you do not have a floating point unit, but you still need to perform floating point computations, and you end up emulating floating point in software, right? Whatever benefits you got from using a simple CPU are lost in the process of converting to floating point and back. The more peripherals that you have, right, you might end up consuming more power because there are more peripherals, but on the other hand you might be able to use techniques like DMA in order to transfer data between those peripherals and thereby get more efficient use of your overall system, right? So, building an optimum or efficient embedded system is not something that can be done by just picking one particular component and then saying I'll write good code for this. It is a system level task. You need to sort of know about properties all the way from the circuit level to the algorithm level in order to get the best possible behavior from your system.